So we were just saying for our self-driving car, the current position is 3 meters, the current velocity is 0.7 meters per second, the current acceleration is 1.8 meters per second squared, but acceleration isn't always constant, right? The robot or the human is applying the foot to the brake pedal, to the acceleration pedal, more or less at different times. So we have to think about what's the rate of change of acceleration, and that's called the jerk. So we can say the derivative of acceleration is the jerk at time t, and we could also say that's the third derivative of position at time t. One of my kids once said to another one of my kids, "Stop being such a third derivative." I might have put them up to it. But what can we do with this jerk idea and our polynomial approximation so far? Let's just choose a number for jerk. How about negative 3.4 meters? What would the units be naturally? Well, acceleration is meters per second squared. Take the time derivative of that, we'll have another per second, so it'll be meters per second cubed. Why would it be negative? Well, maybe this car has noticed a ball rolling into the street from the sidewalk and it's starting to slow down, hoping to avoid a kid or something like that. So it's not actually slowing down at this point. The acceleration is still positive, but it's saying let's use less acceleration, less and less as time goes on. How can we rewrite or change our polynomial guess about modeling position? Let's call it P3 of t. And before we had 3 plus 0.7t plus 1.8 times 1/2 t squared. What do you think we need to do to incorporate the jerk here? Well, it seems like we just keep adding terms. So we'll do plus negative 3.4, and then we might say t cubed. What do you think would happen, though, if we go and check it by taking the third derivative? We would get a 3 coming down, and then a 2 coming down, but then the third derivative wouldn't just be negative 3.4, it would be negative 3.4 times 3 times 2. So we'll throw in a 1 over 3 times 2 here, and that way when we take the third derivative, that term will just end up being 1 times negative 3.4. So we could keep going. There's even names for other derivatives. The rate of change of jerk is called the snap. That would be the fourth derivative of position. The rate of change of snap is called the crackle. And then the rate of change of crackle is called the pop. You might be saying, is that really right? Did some mathematician really take stuff from a cereal's slogan? And all I can say is I saw it on Wikipedia, so it must be true. And I've never seen any other suggestions for what those things should be called. I've heard that when planning the Hubble Space Telescope, NASA included all the terms up through SNAP, which I think for self-driving cars you wouldn't usually do that. You would probably only consider jerk. So let's write that down. There are actually studies that say how much jerk is acceptable in various forms of transit. If you think about it, if you're on a subway car, for example, or a city bus, acceleration or deceleration when there's braking going on isn't bad if you know that you should brace yourself for it, right? If you plant your feet or hold on to one of the posts to counter that force. What the problem is unanticipated acceleration, because then you don't know that you should brace yourself for it and you might end up falling over or something. So there are standards for what makes acceleration unanticipated is changes in acceleration, which would be jerk. So for example, the limit on jerk for public transit by rail is 2 meters per second cubed. And actually there's different limits for forward-backward jerk, side-to-side jerk, and up and down jerk. I can't remember which one this one is in particular, but I'm sure you could look it up if you needed to. Let's take another look at the polynomial we've got here. Let's try to put it in a table form because that's going to be more helpful in the next video or 2 or 3 or 4. Let's make a table like this. We'll have what's our derivative number. So 0th derivative, first derivative, second derivative, third derivative, and you can keep going from there. We're going to leave space for a mystery column that we'll fill in later. So we'll just put question marks here. And then let's say, what's the derivative value now, whatever now is. We were using t equals 0, but it wouldn't always be t equals 0. And what was our derivative value? What was the 0th derivative value for position at time 0? That was 3. What was the first derivative value? That was velocity, so that was 0.7. Acceleration was 1.8. Jerk was negative 3.4. Okay, and then we could say, instead of writing out our polynomial this way, we could write it out with each appropriate term in the appropriate row. So we could say, what's our polynomial term? The 3 was just a 3. The 0.7 was 0.7t. The 1.8 was 1.8 times 1/2 t squared. And then the 3.4 was the negative 3.4. Negative 3.4 times 1 over 3 times 2 times t cubed, like that. Would it be nice to have a system here? Like, why didn't this one have a fraction on it? This one didn't even have a t on it. This t has a power of 2, this t has a power of 3, but this t doesn't have a power at all. So we could make a more systematic version here. Let's see, what could we say? This 3, it didn't have a t at all. Could we give it a t term? But it would have to be t to the power 0. So we could say t to the 0. This would be 0.7. I'm leaving a gap here for the fraction thing. T to the 1. So that way that t has a power on it. 1.8 times 1/2 t to the 2. Negative 3.4 times fraction times t cubed. So what fractions could we put here? This 1 over 3 times 2, 1 over 2, though 3 times 2 is like 3 times 2 times 1, right? Which is a factorial. So I could put 1 over 3 factorial here. What is 2 factorial? It's 2 times 1, which is 2, so that works. So I could say 1 over 2 factorial there. Could I put a fraction here? What would be the most logical thing? 1 over 1 factorial. And then what about here? Well, here the factorial matches the power on the t, so maybe it would make sense to put 1 over 0 factorial there. So we're multiplying all these. But wait, is that going to be divided by 0? Well, what is 0 factorial? Naturally, we might think it's 0, but it's actually 1. Remember that in the previous video we talked about that. So this is a nice way of writing all of those polynomial terms where we have a system where whatever's on the power is also in the factorial in the denominator. So we don't have like t on some terms and no t on other terms and such. Right, so this is a perfectly acceptable way to write a factorial or a polynomial kind of vertically. You can then write it out horizontally if you want to, and sometimes we want to, but don't feel that you have to on some of the homework problems. Next, we'll take this kind of vehicle driving problem and put a pure math spin on it and think about where can we get these numbers from, or whatever these are.